Hi everyone. Today we are going to see the next lecture in the course Cryptography Network Security, that is Euclidean Algorithm. So why we need this Euclidean algorithm is to find the GCD of two numbers. So now we will see why we need to find GCD of two numbers and what is meant by Euclidean algorithm. So generally we'll use this Euclidean algorithm in cryptography to find the GCD of two numbers. So the next topic, that is greatest common divisor. We sometimes in shortcut we call it as GCD. So this GCD will have more value or will use more oftenly in cryptography. And we need to find a greatest common divisor only for positive integers. We're going to find only for positive integers. So let us see an example. So what is meant by greatest common divisor? For example, if you take two values, if I take two values, 2 and 10. Consider we want to find the greatest common divisor for 2 and 10. So generally in mathematics, what we'll do is we'll write all the divisors of 2, we'll write all the divisors of 10. So what are the divisors of 2? So 1 and 2 itself, right? What are the divisors of 10? So 1, 2 can divide 10 exactly. We'll take only exactly divisors, the values which are going to exactly divide them. Okay. Then 5 we can take and 10 itself. Now from these two sets, we'll consider the common values. What are the common values? 1, 2. So from these common divisors, we will choose the largest one as the GCD. So here GCD is what? 2. Here GCD is what? 2. Okay. Now we'll see one more example. For GCD, and then we will see how, if we are given large number of values, how we are going to find the GCD. Okay. So consider if you want to find GCD for the value 140 and the value for the divisor 12. Okay. So these are all the values that exactly divides 140. So starting with 5, 7. Okay, first we'll start with generally with 1. So 1, 2, 4, 5, 7, 10, 14, 70. All these are the divisors of 140. These are all 1, 2, 4, 6, 3, 12 are all the divisors of 12. Now from these two sets, I told you, we'll choose the common values. The common values are what? 1, 2, 4. From these common values, we'll choose the largest one. What is the largest one? 4. Largest one is the 4. So 4 will be the GCD for 140 and 12. 140 and 12. So now, why in this case, if you consider, now we have seen for 2 and 10 where we got smaller values. Now if you consider for 140, how many values you got? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 divisors we got for 140. For example, if there is a question like this, find GCD for 2550 and 268. Consider 268. Now, how we are going to find out? You need to list out all the divisors which are exactly dividing 2500, and you need to list out all the divisors which are exactly dividing 268. From this, again, you need to find the common values. And so consider for how many values you get. So simple, for only 3-digit value, we got around 15. If I considering 4-digit value, maybe I'll get 50 or 60 on odd numbers, right? So it is somewhat difficult. So if you want to find GCD of two largest numbers, so previously a scientist called as Euclid has developed an algorithm to find the greatest common divisors of two positive numbers. Consider two large positive numbers. So here, while Euclidean algorithm, if you're following Euclidean algorithm, basically Euclid has given two conditions or two assumptions. Always given us two assumptions. What are the two assumptions? That is fact 1. That is the assumption 1 is we should consider GCD of a comma 0 is equal to a. A comma 0 is equal to a. Why? Because for 0 it doesn't have any divisors. That's why always GCD of a comma 0 equal to a. And if GCD of a comma b equal to and GCD of B comma R. Okay, and consider second fact is that GCD of A comma B equal to GCD of B comma R. So what is this R? What is this R? The remainder that we get when B divides A. The remainder that we are going to get when B divides A, or when A is divided by B. So these two are the facts that we need to remember while we are learning about Euclidean algorithm, which helps you to find the GCD of any two positive numbers, GCD between any two positive numbers. So again, let us consider the assumptions or the facts. So what is the fact one? Fact one says that GCD of A comma 0 equal to always A, and GCD of A comma B is equal to GCD of B comma R. GCD of B comma R. So what is GCD of B comma R? That is, what is B? So B we know. B is the second positive number that we are considered in the GCD. Then what is R? So R is the remainder that we get when A is divided by B. When A is divided by B. Now we are going to repeat this process. We are going to repeat the second fact until the R value becomes to 0. Until R value becomes to 0, we will continue this process. When R value becomes to 0, whatever the value that is present in the location of B, that will be the GCD of A comma B. That will be the GCD of A comma B. So now let us see that with an example. Then we'll see about Euclidean algorithm. Okay. So I have taken GCD of 36 comma 10. GCD of 36 comma 10. So according to the fact 2, what we should do? So this will be equal to GCD of B. What is B value? B value is what? 10. So 10 comma B value is 10. Now we should write the R value. So what I told you, R is the remainder that we get when this value is divided by 10. So when 36 is divided by 10, the remainder we get is what? 6. Now we need to check whether the remainder is 0. No. So we need to continue this process again. So this will be equal to GCD of, I told you, we need to repeat this process until the R value becomes to 0. So GCD of 10 comma 6 equal to, now again consider this as A and B. Now we should take it as B, 6 comma. So when I divide 10 by 6, what is the remainder? 4. What is the remainder? 4. Now, so is R equal to 0? No. So again, we need to continue this process. We need to continue this process. So this will be equal to GCD of, so it will be A comma B. So it will be A comma B. Now we should write B, 4 comma. If I divide 4 with 6, what I'll get the remainder? 2. I'll get the remainder as 2. Now let us check. Is it 0? No. So again, we need to continue this process. So this will be equal to GCD of B. B is what? 2 comma. If I divide 4 by 2, so 2, that is 2 is exact divisor of 4. So I'll get as 0. I'll get as 0. Now what I tell you, when we get R as 0, stop the process, and whatever the value we have at the location or the position of B, that will be the greatest common divisor of A comma B. So the GCD of 36 comma 10, GCD of 36 comma 10 is what? 2. 36 comma 10 is what? 2. Now let us find whether 2 is the greatest common divisor of 36 or 10, because these two are small numbers, no? By using our previous approach, that is finding all the divisors of 36 and finding all the divisors of 10, and then let us check. So the same way, let us consider the two values. Let us consider the two values. So let us take 36 here. Let us take 10 here. Now write all the divisors that exactly divides 36. So 1, 2 it can divide, right? 2 18s, 3 it can divide, 3 12s, 4, 4, can it divide 4? No, no, right? Yes, yes, it can divide 9. 4 9s is 36. Then 5 it will not divide, 6 6s are 36. Then 7 will not divide, 8, no, 9 already we have taken, right? 4 also divides it, 9 also divides it, right? Next, 10 it will not do, 11 will not do, 12 divides it by 2 times, 12 divides it by 3 times, then 18 divides it by 2 times, then that's it. Half of it is 36. So when we come half of it, there will be no divisor. So 36. So how many got? 1, 2, 3, 4, 5, 6, 7, 8, 9. Now let us write the, so these are the divisors of 36. Now let us write the divisors of 10. 1, 2, 5. Exactly half. Now when we cross half, nothing will be there. It will be 10. So 1. Yeah, the common divisors are 1. Then I have 2 as a common divisor. So 2. That's it. That's it. I don't have 3, 9. I have 5, 10 here. I don't have 5 and 10 here. So from the common divisors, what is the greatest common divisor we have? 2. So the algorithm has given you the correct value. The algorithm has given you the correct value. So now we'll apply the vice versa on these values. That is GCD of 140 and 12. So we'll apply Euler's algorithm on this one, right? So 140, 12. 140, 12. Now 12 tens 120, right? 120. Next 12 11s is 132. 132. So I can take this as, I'll write here, I'll take this as GCD of, so if we take 132, I should take first B 12. And what is the remainder I'm getting here? What is the remainder I'm getting here? 8. Right? 12, 8. Is my R is equal to 0? No, R is not equal to 0. So again, I need to apply the factor 2. So the GCD of B. I'll take 8, 8, 8, So if I divide 12 by 8, what is the remainder? I'll get 4. Is my R equal to 0? No. Again, I need to apply the factor 2. So GCD of B I should take. So GCD of B is 4, 4 exactly divides 8. So I'll get 0 here. So when R is 0, I need to stop the process. And whatever the value I have in the position of B, that is the greatest common divisor. So I'll got from the Euler's theorem, Euclidean theorem, the greatest common divisors are 4. And similarly, by using the normal process, we got the greatest common divisor 4. So this is the proof for Euclidean theorem. This is the proof for we have done. First we have calculated a value and then we have applied the Euclidean algorithm. We got the same value. Similarly, for the example that we have taken in the Euclidean algorithm, we have found the value by using the Euclidean algorithm. Then we have applied the normal procedure and we got the same value. So this is how it works. So this is the algorithm of Euclidean. This is the algorithm of Euclidean. So we'll take R1 equal to A, R2 equal to B. So until R2 becomes 0, this is until R2 becomes 0, we'll take Q equal to R1 by R2. We'll take Q is equal to R1 by R2. That is, we'll take the coefficient and we'll take R equal to R1 minus Q into R2. R1 minus Q into R2. And we take R1. That is, we'll take the first argument as, if I consider I consider this as R1, if I consider this as R1, and if I consider this as R2, what will be the for the next iteration? What will be my R1? My R1 will be R2. My R1 will be R2. So that's what we are taking. R1 will be R2 for the next iteration. and R2 will be my R. R2 will be my R. So what does this R is finding? Let us substitute 36 and 10 here. So R equal to 36 minus, what is the thing I'm getting? 10 into, what is my R2? Sorry, coefficient is 3. Right? So we'll take this as R1. We'll take this as R2. Okay. Now what happens for the next iteration? My R1 becomes the R2. So that's what they have written. R1 equal to R2. Now R2 will be R. Now R2 will be R means R is nothing but our remainder. How we are going to get? So simply how we are going to get is R equal to, we'll take the values 36 minus 3. The coefficient is 3. When 36 divided by 10, the coefficient is 3 into 10. So we know the operator precedence. So the operator precedence, we have the equivalent operators. So we need to do the multiplication operation. Those two are not equivalent. Plus and minus are equivalent, and compared to multiplication, we have the highest priority compared with the subtraction. So it will be 36 minus 30. So it will be 6. So what is the thing we are getting? The remainder. The remainder will be stored in R. So when 36 is divided by 10, the remainder is 6. That will be taken for the next iteration. Now again checks whether R2 is greater than or 0. No, it is not 0. Now what happens for the next iteration? R1 will be R2. For the iteration R1 will be R2. And the value that we get for the remainder as when 10 divided by 6, remainder is what? 4. That will be R. Again, with the R2 will be check. R2 will check whether it is 0 or not. No, it is not 0. Then what happens? Now this R2 becomes R1 for the next iteration, and the value that is we get when R1 gets divided by R2 as 2. So when 6 divided by 4, the remainder is 2. Again, it checks for whether this R2 is greater than or 0. No, it is not greater than 0. So again, here R2 becomes R1 and the remainder will be R. Okay. So when 4 exactly divided by 2, the remainder is 0. So 0. When R2 is greater than 0, when R2 becomes 0, we'll stop it. And whatever the value we are getting in R1, whatever the value we are getting in R1, we'll give it as what? GCD. We'll give it as what? GCD of R1 comma R2 or A comma B is equal to this value. And remember, in this entire process, along with the value, see, along with the GCD for 36 comma 10, we have found GCD for 10 comma 6. We have found GCD of 6 comma 4. We have found GCD of 4 comma 2. Okay. So along with 36 comma 10, we also found the greatest common divisor for 10 comma 6, 6 comma 4 and 4 comma 2 also. The entire process is depicted in this diagram, and the algorithm, Euclidean algorithm, is this one. Okay. So this is the initialization we do. R1 equal to A and R2 equal to B. Okay. So this is how we are going to find GCD when given two large numbers. When you are given two large numbers by applying the Euclidean theorem. Okay. We just found the GCD of numbers 36 and 10. So as I told you that we use Euclidean algorithm to find the GCD of largest numbers. So we'll see one more example. So consider we need to find the GCD of two numbers 2740 and 1760. So if you want to find GCD of these two big numbers, what is the problem is, for example, if you take the common divisors, or we take the divisors of 2740 and 1760 and take the common divisors and find out the biggest of those common divisors, it takes some amount of time. But if you apply Euclidean algorithm, we can easily get the greatest common divisor. So this is 2740, 1760. We know we should consider the biggest as R1 and the smallest as R2. So we have taken it as R1 and we have taken it as R2, right? So from this, we need to derive the values of Q and R. So we know the formula, general formula, A is equal to Q into N plus R. So this is the formula that we follow for the multiplication, where Q is the coefficient and R is the remainder. So that's what we are going to do. So we are going to apply these things now, right? So first take 2740 160. So if you divide 2740 by 160, it goes for only one time. So we'll get Q as 1 and the remainder is 98. Now, what does the Euclidean theorem says? Check whether you have, before going to that, check the value as 0 or not. So it is not 0, R2 is not 0. So we have found the value. In the next iteration, what we need to do is R1 will become R2. R1 will become R2. R2 will become R. R2 will become R. Again, we'll apply the same thing. Now, we are going to divide 1760 by 980. It goes for one time. It goes for one time. And the remainder is 78. And the remainder is 78. So, in this, R is not greater than 0. So, again, we'll make R1 as equal to R2. And we find R2 equal to R. Now again check, R is not equal to 0. R is not equal to 0. Why? Because the Euclidean theorem says you need to continue this process until R equal to or less than 0. So generally we become equal to 0. So now we need to continue this process. So we have done up to 780. Now we have checked 780. It is not equal to 0. It is greater than 0. So we can make R1. So R1 this time becomes to 780. R2 becomes 200. Okay. Again, if you check here, again, for this iteration, R is greater than 0. That is not equal to 0. So we continue this process. Now, 200 divides 780 for 3 times. That is 600. And the remainder is 180. Remainder is 180. Again, so now what we'll do, we'll take R1 as 200. We'll take R2 as the remainder 180. Now we'll check, is R greater than 0? Yes, R greater than 0. Now we'll find Q1 R value. So it divides exactly one time and the remainder is 20. Remainder is 20. Now R1 becomes R, that is we'll take 180 and it will be 20. It will be 20. Now check, is R greater than 0 or equal to 0? Greater than 0. So if R greater than 0, we'll continue the process. So we need to find Q and R first. So Q is 9. So 29, Q is 9. 920 is 180. So the remainder is 0. Now we'll make R1 to R2 and R is copied to R2. Now we need to check, is it greater than 0? No, is equal to 0. Now at this stage, we need to stop our process. We need to stop our process and the GCD of A and B will be in the R1. So GCD of 2740 comma 1760 is equal to 20. Is equal to 20. Now we came from the came to know from the Euclidean algorithm also that, so GCD of 1760980, GCD of 980 and 780, GCD of 780 and 200. So all these space GCD is equal to 20. Is equal to 20. That's what we have learned from the